Yeah, our discussion today assumes you have watched up to lesson 4, and if you take a look in our old tests, which I asked you to do since last week, right? Then there is just 2 more little material from today's that will be in your uh, included in your test 1. So you will see that conditional probability does not show up in my recent test 1. So in the past, like around, let's say around 4 years or more ago, that the last topic in my test 1, is on conditional probability. Now, recently, I think in the last 4 years, I don't include conditional probability in my old tests. Okay, so the last topic was compound event. Okay, so when you study for your test 1, be aware that we don't have conditional probability unless you try to attack my previous test 1 that is like more than 3 years ago, maybe 4 years ago. Then at that time, I still have conditional probability. Okay, which we will study toward the end of today, like in the second half of today's lesson. And it should be the easy ones. Yeah, it should be the easy ones. Okay, now let's start with the inclusion-exclusion formula. Inclusion-exclusion formula. Which our textbook called general addition formula. Inclusion-exclusion formula, or simply our textbook called that general addition formula. Let me just erase this. Now the formula is the following. Probability of A union B is equal to probability of A plus probability of B minus probability of the intersection. That's the formula, which our textbook called general addition formula. Now, why is this true? Let's take a look. When we talk about probability of A union B, it refers to the probability of events that is included in the circles, in these glasses, I usually call that. It looks like 2 glasses. So this is A here, or B. This is A or B. Now, the probability of the union of those 2 events is equal to the probability of event A if you imagine in the Venn diagram, right? Event A plus probability of event B. So the same Venn diagram, but I add just the B part. But you notice that if that's what I do, then my intersection is counted twice. Right? My intersection is counted twice. While in the union here, it should be counted only once. Like this guy plus this guy plus this guy, right? Okay, but when I do the addition like this, notice that this guy plus the intersection, and then B, only B plus the intersection. So the intersection part is counted twice. So to count it only once, I subtract that once. It's double counted earlier. That's why I subtract that once such that it's only counted once. Okay. Now that's why that formula looks like that. And implicitly, we have used this formula here and there when we did the Venn diagram or the contingency table. Okay. Now notice that note, yeah, I need to say that explicitly. Note, we did problems with union even without this formula, without using this formula, explicitly using this formula. Under what situation we did that, Thomas? Please remind us. That is when Venn diagram given or contingency table provided. So if you have Venn diagram, contingency table, you can compute probability of union without using this formula. Thomas, I like formulas. Can I still use formulas? Yes, you can. So you can apply these formulas even to what we did last week. Okay, but you will see it will actually take a lot more time. No need. Okay, so under what situation we will use this formula? When do we have to use this formula? That is when no Venn diagram or contingency table, nor contingency table provided. Okay. Again, is it wrong, Thomas, if I use this formula when Venn diagram or contingency table given to us, like what we did last week, for example? Let's take a look. What we did last week. 26. Where's that? I'm trying to look for. Oh, it's here it is. The one we did here, right? Notice that we compute the probability of union without using that formula, right? That's last week. We compute probability of union without using that formula, union without that formula, right? We did probability of that union without formula. Okay. We basically read it from the Venn diagram, right? Okay, and even when we have contingency table, we did the same thing, right? Okay, so no need to use that formula if you already have the Venn diagram or contingency table in which we actually have a much better visualization of how the data interact. But right now, if we don't have Venn diagram, when we don't have contingency table, then you may consider using this formula. Let's say, for example, an easy one first. Let's say probability of A equals to 0.6, probability of B equals to 0.7, and probability of D intersection is 0.5. Okay, you have to memorize that formula. Okay, you have to memorize that formula and realize that if you know 3 of them, you get the other one. Buy 3, get 1 free. That's what that formula is doing. Okay, so solution. The question is find probability of the union. Then the way we do it, write down the formula first though. Probability of A union B equals to probability of A plus probability of B minus probability of the intersection. So probability of the union is equals to probability of A. So write down the formula first and then you plug in numbers. Okay. So we get probability of A union B is equal to, I think, 0.8. Yeah, because we don't have Venn diagram nor contingency table to refer to. So then we use these formulas. Now the formula, the situation may be twisted around, but we still use the same formula. For example, instead probability of the union, either A or B is 0.9. Probability of A is 0.7. And then probability of D intersection is, let's say, 0.6. Can we find the probability of D alone? Let's find probability of B. Then we use this formula again. Notice that we have probability of the union. We have probability of A. We don't have probability of B. That's what we are looking for. Yet we have the probability of the intersection. So using 3 informations we have, we can find the 4th one. Write down the formula first and then plug in numbers. Is it okay? You usually see this question in the last question in my test 1, usually in my recent test 1. So you see that I'm really nice. I even keep the structure. I just change the numbers, right? Okay, let me compute that. 0.9 equals to 0.1 plus probability of B. So the probability of B is 0.8 again. That's coincidence though. Okay, that's for example 2. Now, let me give you maybe like 3 minutes to do this example. This one's supposed to be easy. This one's supposed to be easy. So let's say probability of A equals to 0.3. Probability of B is, let's say, 0.2. Probability of the union is 0.45. So find probability of the intersection. Okay, let me ask you to do that. I'll give you 3 minutes to do this. Okay, so how do we do this? Write down the formula first. We have a bunch of formulas in statistics. The only time you know which formula to use at what time is by doing enough practice, okay, to overcome the possible confusion, right? So practice more. Probability of the intersection. Now I plug in numbers. Oh, okay, 0.45 for the union. This is 0.3. This is 0.2 minus the probability of the intersection. So 0.45 equals to 0.5 minus probability of the intersection. Let me subtract 0.5. If I subtract 0.5 both sides, I get negative probability of the intersection on the other side. This is negative 0.05. So probability of A intersection B, you multiply both sides by -1, right? You get 0.05. Okay, now that's for this example here. Now let's go on further. Let's go on further. If some variations, if A and B are mutually exclusive, in other words, disjoint, then A intersection B is empty set. Right? That's what mutually exclusive means. Okay, basically, when you have the Venn diagram, when I have Venn diagram, this is the usual view, right? A and B, they may interact, they may have intersection, okay? But the case where they are disjoint, this is the general view, general situation. But if A and B are mutually exclusive, it means they don't intersect. They don't have anything in common. Okay? Now, so because the intersection is empty, then consequently, the probability of the intersection is 0. Now, what is the effect on that inclusion-exclusion formula? Well, the general case, so I copy down the formula we have above. Probability of the union equals to probability of A plus probability of B minus probability of the intersection, right? But if A and B disjoint, then the probability of intersection becomes 0. Therefore, probability of the union equals to probability of A plus probability of B only, right? Because this part here is basically -0, right? Okay. So if disjoint means they don't have anything in common, the intersection is 0, is empty set, then the probability of the intersection is 0. Okay. Now you may remember the case that we had before. Remember the cards, the problem with the cards? a little example. Right? Can you find the probability of selecting, for example, ace or king from a deck of 52 cards? Let's say when we select one card at random from a deck of cards, the 52 cards. What is the probability that we get an ace or a king? And we remember there are there are 4 aces, right? And 4 kings. So we say it's 8 out of 52 at that time, right? Okay, but if you think about this further, notice that, give me a second. I see somebody, anybody raise hand earlier? Nobody. Okay, so we get the answer already. It's 8 out of 52. But if you think about it, how we get that number, if we relate that to this formula, that's equals to probability of getting an ace plus probability of getting a king minus probability of getting an ace and a king at the same time. Right? Probability of getting an ace, that's 4 out of 52. Probability of getting a king is also 4 out of 52. There are 4 kings in the deck of cards, minus probability of the intersection. But there's no intersection. There's no ace that is also king. There's no king that is also ace. Right? That's why then that's basically 0. Okay. In other words, what happened was the king, ace, and king are mutually exclusive or disjoint. So the probability for both of them happen at the same time is 0. That's how we get that 8 out of 52 that fast. Okay, just count how many aces, how many king, and then you put them together, right? Now, that's not the case if, that is not the case when we try to count probability of getting ace or heart. Ace or heart. Now, the thing is, ace and heart are not mutually exclusive. We have one card that is ace and heart at the same time. Okay, so probability of getting an ace, that's 4 out of 52, plus probability of getting a heart, that is 13 out of 52, minus probability ace and heart, there's one such card, right? So this is 4 out of 52 plus 13 out of 52 minus 1 out of 52. That's 16 out of 52. Okay. Yeah. Again, to emphasize there that ace and heart, ace and heart are not disjoint. Now remember, we did this problem, I think 2 weeks ago, without using this formula. Okay, but if you want to relate to this formula, this is what happened. Okay, we still can use this formula. It's just not necessary if you remember what a deck of cards look like. Okay, now let's go back a little bit. with the interpretation. Now, what does probability of A union B means? What does the probability of A union B means? This can also be said as probability of A union B. It can be seen as the probability of at least one of A or B to occur. And you see that it has something to do with question number 3, as I remember in your upcoming quiz that is due tomorrow evening. Okay. Furthermore, another variation, if A and B are independent, A and B are independent. Oh, what is independent, Thomas? We say that, let's write that definition here, definition. A and B are independent if the occurrence of event A does not change the probability of event B to occur, and vice versa. Occurrence of event B does not increase nor decrease probability of event A to occur. Okay. Okay. And so the word independent here, is in the true sense of the word independent we know. It's like if I say that I am independent of that person, so it means I make decision, the decision I make has nothing to do with what that person's doing. That's what we mean by independent. Okay, like for example, if I broke up with my ex-girlfriend, right? Let's say I broke up, and then we said, oh, we are now independent of each other. Okay, we are now independent of each other. Then whatever I do has nothing to do with her, and whatever she does has nothing to do with me. That's what independent means. So if I go to a meeting, or go to a dinner, let's say, and then my friend say, hey, you know what, your ex is inside. So what? It doesn't matter, right? When we say independent, means my presence in that dinner has nothing to do with my knowledge of her presence there or not. Okay. Now to say this, like, well, Thomas, your ex is there, so then when I heard my ex is there, and then I say, oh no, then I don't want to go to that place. Now, it means I'm not independent anymore, because my decision to be present in that dinner, okay, or instead my decision not to attend that dinner is actually affected by her presence. Now that's not independent. That's actually mutually exclusive. Okay, that's mutually exclusive. That's not independent. Okay. Now, when we say independent, means whatever happened to A has nothing to do with B. Whatever happened to B has nothing to do with A. Okay. Now, a little example of independence case. Let's say Thomas toss a fair coin. And Tim, let's say, rolls a fair die. Now, what is the probability that when Thomas tosses his fair coin, what is the probability he has a head? It will be 1/2, right? Okay, what is the probability when Tim rolls his fair dice? What is the probability he get a 6? That will be 1/6. Now notice that if I toss the coin and he roll the dice at the same time, okay, does the outcome of my coin has something to do with his die? You know, there's nothing, no such thing. Okay, so in other words, when I ask you what is the probability Tim actually roll a 3, okay, you don't need to ask me first, Thomas, but I need to know what Thomas get first. Actually, doesn't matter, right? Doesn't matter. We know whatever the outcome of my tossing, when I toss my coin, whatever the outcome, it will not change the probability of Tim having a 3. It will still be 1/6, right? Okay, regardless what outcomes from the coin toss. Okay, that's what we mean by independent. Okay, whatever happened with me has nothing to do with whatever happened with him. Whatever happened with him has nothing to do with whatever happened with me. So even though both of us doing this experiment at the same time, but the outcome of his toss, of his rolling a die, has nothing to do with my tossing a coin. And when somebody asks me, when I ask you, what is the probability I get ahead? You don't need to ask me, but I need to know first what Tim has. No, there's no need. Why? Because we know these two events are independent. Okay, now the thing is, if A and B are independent, we usually denote it this way. The notation is A perpendicular to B. That's the notation for independent. Now, if two events are independent, then give me a second. Now, if event A and B are independent, then probability of A and B is equal to probability of A times probability of B. Okay, if two events are independent, then the probability of those two events to happen at the same time is equal to probability of the product of the probability of each event to happen. So if I look back to this question, for example, then what is the probability when both Tom and Tim toss and roll the die? That will be probability Thomas get ahead and Tim get a 3 is equal to probability Thomas have a head times probability Tim has a 3. Okay, that will be 1/2 times on 6, which is 1/12. Okay. Now, what is the effect of this independence on our inclusion-exclusion formula. Okay, so the general form again is probability of A union B equals to probability of A plus probability of B minus probability of the intersection, right? Now, if A is independent of B, then we basically change the expression for the last term into probability of A times probability of B. Okay, now using this idea, let me ask you to do the following. Okay, I want you to do this example. Let A be independent of B. Probability of A is, let's say, 0.6. Probability of B is 0.5. Find probability of the intersection and probability of the union. Okay, let me give you, let's say, 3 minutes to do this. Okay, anybody can help me what to write here? So what is the probability of A intersection B? Probability of A intersection B is probability of A times probability of B. That is 0.6 times 0.5. That is 0.3. Okay, so this notation again means independent. This is only true if A and B are independent. Then, how about probability of the union? That is probability of A plus probability of B minus probability of D intersection, which we had computed earlier. So we can compute it now also. That's 0.6 plus 0.5 minus 0.3. Right? That 0.3 actually coming from here. Okay. Then this is equal to 0.8. Now this tends to be on the easy side though. This one actually easy side, especially because I asked you what is probability of the intersection first. Now the following is on the hard side. Let A be independent from B. And if probability of B is, let's say, 0.5, okay, and probability of the union, let's say, is 0.7. Find probability of A. Now, this one is more difficult. Solution. We start by writing the formula, right? The probability of A union B is equal to probability of A plus probability of B minus probability of the intersection. Now the thing is, A is independent of B. So the formula being varied, being modified, probability of A plus probability of B minus probability of A times probability of B, right? Then we plug in numbers. This is 0.7. Probability of A is unknown. Probability of B is 0.5. Probability of A is unknown. Probability of B is 0.5. I will subtract this 0.5 to the other side. Okay, so 0.7 minus 0.5 is equal to probability of A minus 0.5 probability of A. 0.2 equals to, now from here, I need you to remember what you learned in pre-algebra, combining like terms. Okay, if you have x minus 0.5x, what is that? X minus 0.5x. Like invisible 1 minus 0.5. What will that be? That's the same to imagine if I factor the x. You don't need to do this though, but I want you to imagine combining like terms. Okay, so that's basically 1 minus 0.5, right? Okay, so when I subtract, I get another 0.5x. Okay, so blah minus 0.5 blah is 0.5 blah. Then probability of A is 0.2 over 0.5. Yeah, you still need to know some algebra. That's the thing. Even though that's not the prerequisite of this class, but the assumption is you have learned that in your high school. Okay, so basically you're supposed to have that kind of background. Then when you use your calculator, this will be, actually you don't need calculator, but if you do, you will find probability of A is 0.4. Okay, now let's try those problems very similar to that. I hope you can replicate that. Let's say, for example, let A be independent of B. If probability of A is 0. Let's say 4, and probability of the union is 0. Let's say 0.7. Find probability of B. Okay, can you try that? Okay, replicate what I had earlier on the top. Let me give you maybe 3 minutes to do this. Okay, let's start. Let's start solution. Probability of the union is probability of A plus probability of B minus probability of the intersection. That's the general formula. And then because A is independent of B, you can skip the first line if you want to. But before anybody asks me a question, but Thomas, why the formula changes? Then before we ask that question, let me answer the question. Okay, that's because we modified the formula to the independent case. Now then I plug in numbers. The probability of union is 0.7. Probability of A is 0.4. Probability of B is what we look for. Probability of A is 0.4 times probability of B. So I subtract by 0.4, I get 0.3 equals to probability of B minus 0.4 probability of B. Now, when you combine these, what you get? Probability of B, let's call that X. X minus 0.4X equals to what? Invisible 1 minus 0.4. 1 minus 0.4 is 0.6, right? 0.6x. This is 0.6 probability of B. Therefore, when I divide by 0.6, both sides, I get 0.5. Okay, now that's for inclusion, exclusion, formula, and all the possible modification. Let me summarize that here, summary. Inclusion, exclusion formula. That's probability of A union B equals to probability of A plus probability of B minus probability of the intersection. You see how much I emphasize you to write down the formula so that you know what is the general form. Okay, general addition formula. You may have this question, Thomas, why do you purposely use different name from for this formula, which is different from our textbook? I'm not saying that the textbook name at the general addition formula is wrong. No, general addition formula. That's just another name for this inclusion exclusion formula. And I'm not saying that you're supposed to use inclusion exclusion formula. No. Our textbook already used that general addition formula, and I just want to remind you that there's another name for this formula. Okay, it's inclusion exclusion formula. If our textbook use inclusion exclusion formula, then I will emphasize the other name also to you. Okay, basically I need you to know how that both of the name. Okay, I need you to know both of the name. Somebody asked me, Thomas, how do you get that 0.6 here? Okay, invisible 1 times blah, which is probability of B, minus 0.4 times blah. You combine like terms, right? That's basically 1 minus 0.4. That's how I get that 0.6 blah. Okay, that's the explanation behind it. Now, make sure you write your leading zero. If you don't write your leading zero, then you will not see that 6. You may see -3 instead. Okay, no, write that leading zero. Okay, now the reason I want to also mention inclusion exclusion formula using that name is to show you how it actually works. Okay, so to get the union, you include those two first. So A and B, so right, the probability of A plus probability of B, you include first, and then you exclude the intersection. Okay, but I'm not saying that I emphasize this name over this name. No. They are actually equivalent. Our textbook used the other name, so I use this name just to complement them. Okay, to complete to your view of that formula. If our textbook had used the term inclusion exclusion formula, then I will tell you this as general addition formula. Okay, so this guy has two names. Okay, I want you to know both names. Okay, now still you need to know that this is general addition formula. This is the general form. Now then the modification happens if we have some special cases. If A and B are disjoint, what happens? If A and B are disjoint, then probability of the intersection becomes 0. Then the formula is then modified to be just like this. Okay, that's the modification. If A and B are disjoint, then you don't need to subtract by the last part because it's 0 anyway. Now, what happens if A independent of B? Both A and B are independent. Then the formula is now modified to be probability of A plus probability of B minus probability of the product of, I'm sorry, probability, the product of probability of A and probability of B. Okay, basically because if the disjoint means probability of A intersection B is 0. If disjoint. So what happened here? Probability of A intersection B is equal to 0. Now, if they are independent, then probability of A intersection B becomes probability of A times probability of B. Okay, that's the summary that you need to memorize. Now, you may know this summary, but still get the question wrong. And if that happens, it's very likely because you confuse the difference between independent and disjoint. Remember, disjoint means they cannot happen at the same time. Okay, while independent means they just have no influence over each other, doesn't mean they are disjoint. In fact, once two events are disjoint, then they are not independent anymore. Okay, that's the philosophical conclusion, right? Okay, if these two people cannot happen at the same time, then they are not independent. Because knowing A happens, we know for sure B cannot happen. Right? Okay, that's for this inclusion exclusion formula. Now, going back to the very top one, just remind you that we don't try to use this formula if you already have Venn diagram or contingency table. Now, is disjoint means dependent? Implied. Is disjoint mean dependent? I think does disjoint mean dependent? The answer is yes. Okay, once we know that two events are disjoint, it implies that A and B are not dependent. However, the converse is not true. However, simply because they are dependent, does not mean they are disjoint. Okay, so these two statements are not equivalent. Is it okay? So your question actually is true. Your conclusion is true. The thing that you asked me to confirm, does this joint implies dependence? That's true. Okay, because knowing A happened, we know for sure B cannot happen. Okay, the definition of independent is that the knowledge of one event to happen or not to happen does not tell us anything about the other event, right? That's what independent means. So this joint, knowing that they cannot happen at the same time, then the presence of one exclude the presence of the others. Okay, now just be careful that simply because they are dependent doesn't mean they are disjoint. Okay, like for example, like me and my wife is so dependent of each other. Okay, I can't even say that I depend on her so much more. Yeah, I depend on her so much more than she depends on me. I mean, it's like I really think that she can live without me. I don't think I can live without her. How do I? How do I live without you? Yeah. Yes. You see that we are dependent of each other, but at the same time, we are not disjoint, right? Okay, we are not disjoint. In fact, uh, everywhere you see her, very likely you see me. Everywhere you see me, you see her. Okay. Okay. So we are dependent, but we are not disjoint. However, once we are disjoint, for sure we are dependent. Okay. I hope that explains that. Okay. But very good question. That's a very, very good question. Let me go on to the next topic, compound event. This one is, in my opinion, is fun. Okay, but of course more complicated. Okay, more complicated, fun, yet solve more problems, and we are getting into counting cards eventually. But let's do that first. Like I use example from counting cards. Where's mine? I use example from counting cards. Let me quote this: a deck of cards. Long time no see. Okay. Now we get used to ask the question, to answer the question, if we select one element, if we randomly choose one card, find the probability of getting a king, find the probability of getting a diamond, find the probability to find king and diamond at the same time because we don't select one card, right? And find the probability of getting king or diamond. Can I ask you to do this first? Maybe 3 minutes for this. Okay, let me give you 3 minutes to do this problem. Supposed to be easy though. Okay, especially if you're already someone who play cards. The only time I usually have issue when I use examples from cards is when I have high school student or younger in my class. Why? Because they are not supposed to talk about cards yet, I was told, right? I mean, if my son already like around 10 years old, I will play cards with him. I don't mind. So it's not gambling. It's like simply because you play with cards doesn't mean you gamble. But of course, when you gamble, very likely has something to do with cards. Okay. But yes, I have encountered some students in my, especially my Saturday class. So in the past, I usually assigned to teach on Saturday instead of Friday. So at times I have high school students or even middle school students. They were the ones say, "Oh, Thomas, what is a deck of cards?" But once I show them this and see how it is being played, they get interested and they actually master a deck of cards more than other students. so, so if this is the first time you see a deck of cards, please don't get discouraged. Okay, every students who have seen this before can do this actually quite well. Now, let me ask you to do these 4 problems first in 3 minutes. So what is the probability of getting a king? There are 4 kings out of 52 cards. We reduce to be 1 over 13. How many diamonds? Probability of getting a diamond, there are 13 diamond cards. So the probability will be 13 out of 52, which give us reduced to be 1/4. Probability of the intersection of king and heart, king and diamond. Or we can simply say this is probability of getting king diamond, diamond king. There's only one such card. So the probability will be 1 out of 52. Now then, how about the probability of the union? Either a king or a diamond. Okay, king or diamond. Now you see that there are 16 such cards. However, if we count the yellow one first, there are 4 such cards. If we count the blue ones, there are 13 such cards. The sum is 17. Now that's because this king diamond is counted twice. Okay, that's why we need to subtract that once. Okay, so this will be equal to 4 plus 13 minus 1 over 52. That's 4 out of 13. Okay. Now, if you remember, this is basically probability of getting a king plus probability of getting a diamond minus probability of the intersection. That's what we actually did. Okay, without applying the formula, but we apply the concept. So I try to sneak in the concept first before I use the formula, because if we start with formulas first, sometimes it's just like we don't know how the formula comes up with that. So I try to explain the concept first, and especially I also believe that most of you are pretty good with your intuition. Okay, now compound event, however, is for such situation. Instead of selecting one card, suppose we let's say we select 3 cards. Okay, 3 cards without replacement. Suppose we select 3 cards without replacement. Sometimes we can also say 3 different cards. Now, what is the difference between without replacement and with replacement? Now, without replacement means the following. Suppose I pick 1 card, right? I need to pick 3 cards, but suppose I pick 1 card and that 1 card is this one. Okay, then the next selection will choose from only 51 cards, not 52 cards anymore, because I didn't put this back. I don't put this back. The cards that already selected do not be put back into the deck. Okay, that's what it means to be without replacement. Now, the effect is then if you do it without replacement, then you will not be able to select the same cards again, right? Okay, then the cards you select must be different. There's no possibility of selecting the same card again. That's why one of the hint of no without replacement is by using the word different. Okay. In practice, when we say select 3 cards, it actually means this one. Even if I don't use the phrase without replacement, even if I don't use the word different, it means just this. If I want to select 3 cards with replacement, then I need to say it explicitly. Okay, now suppose we have this. Select 3 cards without replacement. Or another way to say it, suppose we select 3 cards, 3 different cards. And the first question, find the probability that part A, that all are aces. Find the probability that all of them are aces. Now, even though we select 3 cards, we can see the selection as being done one by one. So probability that 3 aces, right? What is the probability the first one is ace? Probability that the first is ace. That will be 4 out of 52, right? Now then, after you get that one card, you set it aside, you don't put it back to the deck, it's without replacement. Then what is the probability that the second one is also an ace? Then how many aces you have left? How many aces you have left in the deck? 3, that's right. Out of how many cards left? 51, right? Now then, after you get these 2 aces, you don't put it back to the deck. What is the probability that the third one is ace again?
250.
2 out of 50, that's right. Okay, now then from there you compute the probability. Usually I ask you to convert this into decimal. So 4 over 52 times 3 over 51 times 2 over 50. That is, oh, that's a small number, 0.00018. I use my calculator and I see this. I see 1.80995 blah 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 e to e negative 4. Now, if you see this notation, this is calculator notation for scientific notation, which actually means 1.80995 blah 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 times 10 to the negative 4. Okay, that's what it means. Now, however, in my class, I want you to still write it in decimal, right? You can write this first. You can write this first. You can write this first. But then you need to also write this after that. Okay, now what does it mean to have 1.8 something 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 times 10 to the negative 4? It means the 1 here, okay, the 1 here is at the 4th decimal place. The 1 is at the 4th decimal place. That's how we get that 0 point, the first decimal place, the second decimal place, the third decimal place, and then 1. 8, 0, 9, 9, 5, blah, blah, blah. Okay, that's the explanation of this calculator notation. Now we round it to only 5 decimal places. That's why I write 0.00018. But the 1 is at the 4th decimal place from what you see on your calculator. Now your turn. Can I ask you to find the probability that all are hard? So that's the probability of getting 3 hard cards. Equals to what? Now how about probability of getting Jack, then Queen, then King in that order? So that's probability of Jack, Queen, King. When you play pokers, like you basically deal with 5 cards with some variations. It's basically selecting 5 cards without replacement. Yeah, right now we do 3 cards first. Okay, can anybody help me with part B? Find the probability of having all our hard cards. How many hard cards we have? 13, huh? So the probability the first one is hard is 13 out of 52, right? That's the first hard card. And then over 51, right? That's the probability of getting another hard card. That's 2 hard cards so far, times 11 over 50. Okay, so 13 times 12 times 11 divided by the product of 52, 51, 50. I get 0.012941. So it's actually quite unlikely, but the probability of getting 3 aces is actually a lot lower. How about probability of getting Jack first, and then Queen, and then King? So how many Jacks? There are 4, right? 4 Jack out of 52 times, after you get a Jack card, you set it aside. What is the probability of getting Queen next? How many queens in the deck now? There are 4 queens out of only 51 cards because you took 1 Jack out already, right? Times, what is the probability of getting a king after that? There are 4 kings out of only 50 cards. There will be 4 to the power of 3 divided by the product of 52 times 51 times 50. Ooh, that's a small one. I see this on my calculator. I see 4.8265 blah 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 e to the negative 4, which is 4.8265 blah 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 times 10 to the negative 4, which means this 4 here starts at the 4th decimal place. That will be 0.8265 1 decimal place, 2 decimal place, 3 decimal place, 4, 8. Okay, so the probability is very small to get Jack, Queen, King in that order. So if you get King first and then Queen and then Jack, it doesn't count. It doesn't count. It's not that one. You need to have what the question here says, that is Jack and then Queen and then King. Now, once we are done with our test 1, which is 2 weeks from now, okay, next week we will cover material that is not in our test 1 though. It's already new material, but once we are done with that, so next week I plan to tend to be on the easy sides, I hope. Okay, well, no, it's not that easy though. It won't be that easy. But then after your test, then I start to do problems where the order doesn't matter. So at that time, the question will be, what's the probability of getting a Jack, a Queen, a King in any order, regardless the order? Then the computation will be slightly different. Okay, we don't do this technique anymore. Now, next, I would like you to do the following question. Part D, find the probability of getting no, maybe no king. So all 3 cards, none of them kings. And then next one, probability of no club or no clover. Once you're done with that, then later on we can find the probability of at least a king, or at least 1 king. Okay, and then part G, at least 1 club. Okay, let's do this together with our little break, 10 minutes break, 10 minutes break plus, let's say 5 or 6 minutes, let's say 7 minutes. We come back at 10:10. We come back at 10:10. At 10:10, we are done with these 4 questions. Now, part D, what is the probability that of this card, of these 3 cards, none of them king? So before we start, let's count first. How many king cards? We know there are 4 kings out of 52, right? So the number of not king will be 52 minus 4, that is 48. Right? Now then, the first card to be not a king is 48 out of 52 times not a king again. They are only 47 out of 51. Then not a king again is 46 over 50. That will be 46 times 47 times 48 divided by the product of 51 and 52 and 50. I get 0.78262. That's for part D. Part E, what is the probability? No club. How many club cards? The number of club cards is 13. Okay, so the number of cards that is not club will be 52 minus 13. There are 39 cards that is not club. So the probability that the first one is not a club is 39 over 52 times uh, 38 over 51 times the third card, which is not club, will be probability is 37 over 50. That will be 39 times 38 times 37 over the product of 52, 51, and 50. That's 0.413529. So I round it to 3. Now part F and G are classic questions that usually see not in our textbook only, but also in my test. What is the probability of at least one king? Probability of at least one king, that's equals to 1 minus probability of no king. See, when you take 3 cards, right? Then the possible outcomes either no king, 1 king, 2 kings, or 3 kings, right? Those are the possibilities. Now, what they want here is at least 1 king. At least 1 king. Now, the thing is to compute at least 1 king, there are 3 events that we need to compute, and they are actually very hard to compute, except the last one, probability that all of them king, we already computed in part A. Right? We already compute that, very similar to part A. Okay, but to get only 1 king or only 2 kings, that's very difficult. Now, instead of computing it that way, let's compute the complement. Okay, compute the complement and subtract that from 1 later on. Now, the thing is, we already compute the probability of no king in part D, 0.78262. That is 0.21738. Okay, so instead of attacking at least 1 king, like 1 king, 2 kings, 3 kings, we look at the complement. Okay, we look at the complement. The complement of at least 1 king is no king. The complement of at least 1, I mentioned this in my lecture, but let me mention that again here. Okay, the statement at least 1 is the same to the statement some. At least 1 also implies some. So when we say anybody in that room or some people in that room, means at least 1 person in that room. When we say, oh, something wrong with that person, then you mean at least 1 thing is wrong with that person. There's something wrong with Thomas. There's at least 1 thing wrong with Thomas. Okay. Now the complement of that, the negation of at least 1, the negation of some is none. So when you say something wrong with Thomas, to negate that statement, you will say nothing wrong with Thomas. Okay. Yeah. This also represent, I usually say this, the word never is the complement at least 1 at the sum. So when my wife say, you never help me doing the laundry, then all I need to tell her, remind her, is that at least I did it at least once. Okay, Thomas, you never helped me with the laundry. I did. I did it at least once. Remember when we bought this machine? I show you how to use it. Okay. Only that one time. Well, at least you can never say never anymore. Okay. Now, the thing is another one. What is the complement of all? the complement of all is some not. That's the complement. Okay. The complement of all is not none. That's a lot of misunderstanding. Okay, that's the type of misunderstanding that is really, really bad. Okay, the complement of all is not none. That's overkill. Now, let's illustrate it this way. Let's illustrate it this way. I think this is the illustration I use in my lecture too. So you have a car with 4 doors. Some people call it 5 doors, include the back, the door at the back here. Okay, but let's say you have 4 doors. We say that your car is locked. Car is locked if all doors lock. Now we know that fact. We say that is your car's locked. It refers that are all the doors locked. Okay. Now then, what is the complement of lock? Not locked. The car is not locked if, should they say that that car is not locked if all doors are not locked? Actually, no, you don't need all doors to be unlocked. You just need one of them not locked. Okay. If some doors are not locked, some doors are not locked. In other words, at least one not. So you know the following is an absurd statement. If somebody says, well, my car is locked, at least most of the doors are locked. No, doesn't matter. Once you have one of your doors not locked, then your car is not locked. You cannot use the sense of majority there. Majority of the doors locked, so the car is locked. No, I mean, okay, if you put yourself as a thief, then that's all you need, right? That's all you need. You just need one door not locked. Now, of course, right now we say that most of the cars already central lock, right? So if you press lock, then all the doors are locked. It is true, but still, that when a thief want to play with your car, then all they need to modify it is one door, right? I mean, another way to say that, like if a burglar, if somebody wants to steal something from your car, they don't need to open all 4 doors. No, they just need one door. And sometimes it's window first, right? They break your window and then open one door. That's all they need. Okay, so it is a joke when somebody say, it is a joke, really, a silly joke, right? Okay, when somebody have his car break into, and then the owner still say, well, this thief is stupid. Okay, he only opened one door. Okay, if he actually opened 4 doors, then he can take a lot more things in my car. Don't you think that's right? No, they just need one door to be unlocked and and exhaust everything you have in your car. Okay, they don't need to open 4 doors. Okay, yeah. So using this idea here, using the idea we have here, then we are able to make use of the complement in answering questions. Okay. So the last one here. What is the probability of at least one club? At least one club. Now that's the same to 1 minus probability of no club. But probability of no club is something we already computed in part E. That is 0.41353. That's equals to 0.58647. Okay, that's for this compound event without repetition, without replacement, I'm sorry, without replacement. Now, what I want to do next is we will do the same problems again. Okay, exactly the same problems, but this time we do with replacement, and I want you to see what happened with the work. Okay, let's do that. Suppose we select 3 cards from a deck. Select 3 cards with replacement. Okay, you put it back, right? Okay, part A, find the probability that all of them, find the probability that all are aces. Find the probability that all are diamonds. Find the probability of getting Jack, then Queen, then King. Find the probability of, what is that? No King. Find the probability of no club. But we will do the first 2 questions first, and then the rest I will ask you to do it. Okay, what is the probability all are aces? Remember, we do it with replacement. What is the probability? The first one is ace. The probability the first one is ace is 4 out of 52, right? Now, because you put that ace back, how many ace you have left in your second draw? Like when you selected the second time, you select from how many cards and how many aces at that time. You put it back, right? After you pull an ace, the first draw, the first time you pull the card, you got an ace, you put it back to the deck. So for the second draw, the second time you pull the card, you still have 4 aces out of 52 cards. And likewise, for the third time you do it, after you get the second, you get the card the second time, right? You still put it back. What is the probability that the third card still an ace? That will be 4 out of 52. Okay. Before I go too far, I want you to realize this. Because you put the cards you already selected back, then for your second drawing, the situation will be independent of whatever you have in the first draw. Okay, so because let's say this is the pool of cards, right? There are 4 aces, right? You pull 1 ace out. Oh, that's an ace. Okay, then before, if we do it without replacement, then after that, you only have 3 aces left to select from, right? Out of 51 cards, not 52 cards anymore. Now, but if you do with replacement, if you do it with replacement, you get that ace, you put it back, right? So for the second draw, when you pull another card, you actually start with the same situation with what you did earlier. The deck has not changed. Okay, that creates the independence case. Basically, the probability for you to get an ace the second time is independent of if you get an ace first time or not. Right? The probability that you get an ace at the third draw is the same to the probability you get an ace in the second draw is the same to probability you get an ace in the first draw, because the situation for each time you draw them are exactly the same. It's still 52 cards and 4 aces in there. Not the same to when you do it without replacement. When you do it without replacement, the first ace you took have to be excluded from the second draw. You don't put it back. Okay, now you see that if we do it with replacement, then it creates dependence. I'm sorry, independent case. Okay, therefore you see that there's no change in the probability if you ask for the same event. Okay, so with replacement, the probability of getting the first ace is equal to the probability to get the second ace is the same to probability to get the third ace. That will give us 0.000455. So I make it 6 here. My calculator show 4.55 something e to the negative 4, which means 4.55 something times 10 to the negative 4. Okay, now that's for probability of getting 3 aces if the experiment or the procedure is done with replacement. Okay, what about probability of getting all diamond? And how many diamond cards we have? There are 13, right? So the first card, the probability to be diamond is 13 out of 52. The second card, because you replace it, then you still have 13 out of 52. You still have 13 out of 52. Okay, so there will be, the probability will be 0.015625. Okay, now let me ask you to try the rest of the problem. I do have questions with replacement cases, but that will be mostly in my test 2 instead of test 1. Okay, you will see this type of question. Actually, the question you have in your test 1 will be the type without replacement. Okay, but in your test 2, you will see the case with replacement. Now, we don't really discuss this in our test 1, the one with replacement. We do a little bit just for the purpose of you knowing the basic, but when we start talking about this more intensively later, that's because it has something to do with binomial distribution. Binomial distribution, that's in chapter 6 in your textbook. Okay, this is chapter 5, right? It's chapter 5, the middle of chapter 5. Now, later on, 6.2, so something we will cover either next week or 2 weeks later. That's in has something to do with this, because the event between the first and the second and the third are all independent. Then it becomes binomial distribution. Don't worry about that right now. Right now, just do it one by one. Okay, just do it one by one. Okay, so let me ask you to do the rest. What is the probability to have Jack, then Queen, then King, if it is with replacement? Probability of no King, probability of no club, and part F, a probability of at least one King. and probability of at least one club. Okay, let me give you 5 minutes to do this. So part C, probability of getting Jack, then King, and Jack, then Queen, then King. That will be 4 out of 52 because there are 4 Jacks out of 52 cards. And then there are 4 Queens out of 52 cards because you put it back, right? If you don't put it back, then you will have 4 Queens out of 51 cards. Okay, and then King will be 4 out of 52 again. The result is 0.00046. Notice that this is the same configuration with 3 aces. Okay. Part D, probability of no king. There are 48 cards, which is not kings. If you don't put it back, then the second draw, you will have the same probability. The third draw also the same probability. Okay, so that will be zero point 78657. Let me round it to 3. Part D, probability of having no club is, how many club cards? 13, so 39 without 39 not club cards. That would be 39 over 52, 39 over 52, 39 over 52. Almost no fun, huh? That is 0.421875. Now, probability of having at least one king will be, that's probability at least one king, that's equal to 1 minus probability of no king. Now, probability of getting no king is 0.00046. So the probability for you to have at least one king is, oh, I'm sorry. No, I put a wrong number. The one next door here. 0.78653. That will be 0.21347. Okay, a probability of at least one club, that's 1 minus probability of no club, that's equals to 1 minus 0.42188, which is 0.57812. Now I start this lesson with a deck of cards, right? Now you will see that we will focus on the one without replacement, even though you still need to know how to do the one with replacement. Okay, as you can see, the one with replacement, the case with replacement is a lot easier. Okay, even though we will go a lot deeper in future. Now let's go on with what if we have, for example, contingency table, or let's do Venn diagram first. Let's do Venn diagram first. Suppose I have this, for example, I have this Venn diagram. Okay, I have set A and set B. Set A and set B. Okay, I have 5 in the intersection, let's say 12 only in A, and then let's say 13 only in B, and then we have 10 outside of all those. So in total, we have number of element in this is 12 plus 5 plus 13 plus 10. That should be 40 in this case. Now what we will do is the following. Okay, let's say we will select, let's say we select 4 elements from this Venn diagram at random. Let me emphasize that without replacement by saying 4 different elements. Therefore, then we won't be able to select the same element twice or more. Okay, suppose we select 4 elements at random. I want you to compute part A. Find the probability of selecting all 8. All of them from part A. By the way, you need to know this already. How many elements we have in A? How many elements do we have in A? Nobody's answering me. I wonder if you don't hear me or you just pay no attention. No, we have 12 elements in A only, but we have more than that. 12. We have 17. That's right. We have 17 elements in A. Okay, 12 of them only in A. So the way we see this Venn diagram is that the number of element in A is the number of element in that circle A. Okay, that's how we get that 17. There are 17 elements in A, 12 of them not in B. Okay, so I think one of you have that question earlier today, Thomas. I tried to do the Venn diagram, but something not right. That's because you didn't read the problem or misunderstand the problem from what it says. Okay, now the way we read this here, okay, there are 17 elements in A, 18 elements in B, and 5 in both. Okay, so for the person who asked me that question earlier today before the class, Thomas, I tried to do the quiz 234. Is it quiz 234? Yeah, I think so. Quiz 234. But even when I did part number 1A, I don't think I did the Venn diagram correctly. That's because you are reading into the question. When we say 17 in A, it doesn't mean 17 here. No, no. Okay, no. It means 17 in that circle. Okay, there are 17 in that circle. Now, 5 of them in the intersection, which implies 12 of them outside of that intersection. Okay, but still, we need to have 17 elements in part A. Okay. Now then, what is the coming back here? What is the probability that all 4 elements that we select here, all of them from A? Then that will be 17 over 40 times. It's different elements, right? Means we cannot, once we select that first element, we don't put it back. Okay, now we have only 16 elements in A out of 39 in total, times 15 out of 38, times 14 out of 37. Now, everything after this is your calculator skill. Next, I would like you to do probability of all 4 are from B. And then probability that none from B. And then probability that at least one from A. Okay, let me ask you to do these 3 problems. I think I can give you 5 minutes from now. Okay, but the idea is still the same though, okay? The idea is still the same to what we did with the cards. Right now, we have a better summary. Okay, I give you 5 minutes. I would like you to compute this also using your calculator. Okay, go ahead. I need to compute that one first. 17 times 16 times 15 times 14 divided by the product of 40 times 39 times 38 times 37. That will be 0.026. Give me a second. Oh, 0.02604. What is the probability that all of them be? So there are 18 B's in the group, right? In that box in the Venn diagram. 18 times 17 times 15 times, 16 over 38, 15 over 37. So that will be 0.03348. Part C, what is the probability that none of them from B? How many not B? There are 12 plus 10 not B, right? 12 plus 10 not B, there are 22 not B. So that will be 22 over 40 times 21 over 39 times 20 over 38 times 19 over 37. I will compute that. That gives me 0.08, 0.08004. The hard one is at least one from A. At least one from A means 1 minus probability of no A. Now we need to compute that first, probability of no A. Probability of no A will be 1 minus, how many no A's? How many outside of A? Outside of A, there are 13 plus 10, there are 23 outside of A, right? 23 outside of A. Let me see. Is it the same, similar to, I don't know. Will this be similar to quiz 2, 3, 4, question number 5? Maybe. Yeah, I think as I remember, question number 5 is it contingency table? Let me finish this question first and then I see quiz 2, 3, 4, question number 5. Okay, yeah, let me finish this first. So 23 outside of A. So that will be 23 over 40 times 22 over 39 times 21 over 38 times 20 over 37. Okay, this is the probability of no A. Now then 1 minus that will give us probability of at least 1 from A. Let me compute that first. I get 1 minus 0.09689, which will give me 0.90311. Okay, that's for this question. Let me take a look on quiz 234, number 5. Quiz 234, number 5. Yes, it's actually very similar. It's actually very similar. Yeah, but the question, quiz 234, number 5, it's applied to a deck of cards. Okay, so it is actually more similar to my very first example. Very similar to the one here. Okay, but in quiz 234, instead of selecting 3 cards, we select 4 cards instead. Okay, yeah, 4 cards instead. And in quiz 234, let me see again. Yeah, we select 4 different cards, right? So it is without replacement. Okay, so it is without replacement. Good that you observed that. It's similar to number 4 for part C and D. Okay, now that's from our quiz. Let's see further. Now, one of the question, I believe that's question number 2 in your quiz, has something to do with the alarm, I think. Okay, but of course I will not answer that directly. Okay, I will use something similar to that. Okay, suppose, for example, on the other hand, yeah, suppose, for example, on the other hand, the probability that a connection line is down is, let's say, 0.94. Oh, that's a high probability to be down. Oh, let's change it, 0.06. So in other words, the probability that the connection is good if you have only one line is 0.94. Okay, so connection from one point to another point, the probability that it is working is 0.94. The probability that this one line is not connected for whatever reason, let's say the weather or the electricity or the flood, or is lightning down, it's down because of lightning, is 0.06. Now, even though 0.06 may seems to be a small number, the probability is small, but it also means that out of 100 instances, 6 of them bad. Right? Imagine if that happens to me as a teacher. Every week I need to teach how many days? 1, 2, 3, 4, 5, 6, 7, 6, 10, 11 times. Yeah, there are 11 classes I need to teach every week. Yours only 1, but I have some classes that I have twice a week, right? Okay, a total of 11 times I need to teach, right? Now, it means in 10 weeks, approximately 6 of them down if this is the probability, right? Okay, I just do the rough estimate. Okay, but imagine if out of 100 meetings, 6 of them down. Well, of course, with that situation, I will have enough student file complaint against me, right? Even though actually it's not my problem, it may be because of the spectrum problem, right? The internet connection. Okay, now so from spectrum point of view, even though 6% seems to be low for most people, but if you do it too often, then you will have enough number of down if you rely only on one connection. So what spectrum is doing is the following. You have a couple ways to improve this situation. One way is to improve this connection line. Okay, one way is to improve this connection line. But the thing is, like, the technology that we use, like even if we try to use a newer technology, the improvement will not be that much higher though. And let's say it becomes 0.98, right? Let's say it becomes 0.98. So the probability that this line is down is 2%. So out of 100 meetings, on average, 2 of them will be down. It's still not good. It's still not good. Now, another method to improve this connection, is instead of just upgrading the router, let's say, that's one way, but that's not the only way. Let me offer you a better way. A better one is to build a parallel connection, even though with the same technology. Okay, believe it or not, even if, so I want you to compare this. So one, we have connection with 0.94, but only one line. Okay, compare that to the following situation. So let's say I am a new company, right? I use old technology, so the router I use is an old one, or connection line I use is a bad one, with probability that being good, the probability being good is only 0.9. Okay, so the probability that this connection to be down is actually 10%. It's worse, right? But I use old technology. However, I do parallel. Instead of only one line, I use 2 lines. Okay, so think of it this way. If I use the newest router, it cost me maybe $200 per deadline, right? Okay, the probability that it is down is 6%. Now then, Thomas come up with a new method. So Thomas make a new company and offer this kind of connection. Okay, I purchased old routers from those companies, the old one. I don't use the newer technology, I use the old one. So the router I use maybe from 10 years ago, but instead of using one connection, I use 2 connections, parallel connection, such that even if this is down, I still can use this one. I'm still connected. Or even if this is down, I still can connect. I'm still connected this way. Okay, now imagine what is the probability that my connection is down. My connection will be down if both of them down. Okay, so I use the blue one right now. What is the probability? Find the probability. The probability that parallel two parallel connection will be down. A 2 parallel connection given knowing probability that it is good for each connection is 0.9. So let's see. Solution. Probability that the connection for one line is good is 0.9. So the probability that one line is down is 1 minus 0.9, which is 0.1, right? That's for one line only, one line. Now then we look at the two parallel lines. What is the probability it's down? Now the probability that this line is down, this two parallel lines down, is when both of them down. If probability that both lines are down, that will be 0.1 times 0.1, that's 0.01. Now then the probability that it is connected will be 1 minus probability that both down. That's 1 minus 0.01, that's 0.99. Now you see, okay? You can have the newest technology, but still less reliable compared to my method. In other words, do not always blame the technology. Okay, we don't need a good technology to improve our connection. We actually have another way to do that. Okay, in my other class, I explained the following. 20 years ago, if you already born at that time and already used cell phone, 20 years ago, our connection, our cell phone connection was actually still not as good as the one we have right now. Why? Because at that time, maybe Thomas is here, okay? At that time, we don't have enough cell phone towers around us. Okay, let's say only 2. But the thing is, we have too many people using cell phones already even 20 years ago, such that, and the technology is still quite odd, such that it is possible that 4 or maybe 40 people attacking or using one tower at once. And all of a sudden, we get busy signal. Okay, but right now, we have basically a much better tower, cell phone tower, much better cell phone towers, and a lot more. Okay, you may not realize that you have cell phone towers in your area, but there are actually a lot more. Most of them looks like a tree. Of course, some others actually being posted at some building, right, inside the building. But usually is with antenna. But the one, let me show you. Where's my website? Let me show you cell phone towers that they usually, what you call that? What is the right word for that? They usually decorate that such that it doesn't look like cell phone tower. Now, when you drive, you may see this, but do not try to look for it, okay? Only when you have a red light, when you are stopping for a traffic light, then you look around, but don't try to look for it, okay? Cell phone tower. That's what it looks like. These are what cell phone towers look like, okay? Now, 20 years ago, we don't have a lot of this. Right now, we have a lot more. Okay, now at West LA College, if you went to West LA College before, we are actually next to oil mine, such that they don't have a lot of cell phone towers in our surrounding area, such that the signal at West LA College not as strong. Now, East LA College, on the other hand, is nearby a business center, right? We have Atlantic Square across Atlantic. Even on our side, we have McDonald's, we have Yoshinoya, we have, I think, Burger King, right? Basically, it's a pretty crowded shopping center, such that we have a lot more tower. But in the past, we don't have that much. Now, what you don't see are things like this. Do you see this? This is actually a cell phone tower, but they decorated in a way that it doesn't look like a cell phone tower. Okay, they disguise that as a tree, and we have a lot such thing though. You see this one? Oh no, this is the cell phone tower, but next to it they have a tree. No, not that one. Something looks like this. See this? Right? This is actually cell phone towers, but they disguise that. You see nothing? Hold on. Oh, sorry. Here. Sorry. This is the cell phone towers that this guys. It's supposed to look like this. It's supposed to look like this. Do you see that now? Okay, yeah, it's supposed to look like this. But the thing is, like, if you have too many such thing in our area, it feels like, oh, you know what? No more trees in our surrounding area. It's like all cell phone towers. Okay, so some people, some cities decide, oh, you know what? Let's decorate that such that it doesn't feel like we have only towers. We have trees also. So they disguise that. They disguise that becomes like this. So you see, this is a fake, so fake a tree. You see this a lot actually in Las Vegas, this type of cell phone towers. Okay. So in the past, we don't have that much. Right now, we have that a lot more. Yeah. Okay. Now, at East LA College area, I refer to East LA College because we are at East LA College, right? Okay. At East LA College area, because we have a lot of shopping centers and less trees, they usually just attach that to some building antenna from a building. So usually a building have antenna already, right? So they just attach that. At West LA College, for example, or in the surrounding area. Also, as I know, around USC and Cal State LA, okay, they have a lot of trees there. Now, some of the trees, they disguise it this way. Okay, some of the trees, they discuss it that way. This one also, you see. Okay, it seems like a cactus, but it's actually a tower. Okay. They camouflage that, they disguise that. So the look is quite deceiving actually. Let's come back. Okay, now, because of we have more cell phone towers, then our cell phone, so the connection can handle more people making calls at the same time. It's basically right now at this point of time in LA, we have more people using cell phones than landline. Okay, why? Because we have more towers, and the towers right now is even better than 20 years ago. At that time, it's only 1 or 2Gs. Right now, we have more 5Gs. Okay. As I know, every 1G increase, it represents at least 1,000 times faster. At least 1,000 times. Now, we have 6G's connection coming in 2 years. So, in 2 years, our internet connection by smartphone will be at least 1,000 times faster. Okay, that also improve at the same time the reliability. Okay, now let's go back. That's for the compound events. We will see more compound events in future. Okay, but for now, let's just leave it here. Okay, let's just leave it here, and then let's move on to, you know what, I don't really want to do conditional probability right away, but I guess I already covered everything you need for your test one. So the material for test one, the material for your test one ends here. Okay, now what I'm about to do next is to do conditional probability. And then I think I will cover conditional probability in 1 hour. And then we go on with problems from our textbook regarding compound event and conditional probability. I think that will be 5.2 and 5.3. Conditional probability in our textbook, as I remember, is 5.3. Okay, what is conditional probability? Again, I assume you already watched the lecture from lesson 4. Okay, so 5.3, conditional probability. It's already in my lecture video, but let me redo it again here. The definition. Probability of event A, or simply probability of A, given B, event B occurs, is denoted by probability of A given B. Let me move that to the middle. Is denoted by probability of A given B, where the B that you write after the vertical line is the condition. And this is the desired event. Okay, now an example. I hope this one is still a bit abstract, but I think if you can imagine it, that will be great. Okay, suppose we have select a card, select one card from a deck. A deck of 52 cards. Now, what is the probability that it is a king? If you select one card and I ask you, what is the probability that card is a king? And we know that will be 4 out of 52, right? Because there are 4 kings of 52 cards. We can reduce this to 1/13. But the probability of getting a king is different if I tell you that it is a face card. So you select a card, right? And then you happen to know that's a face card. You happen to know that's a face card. You look at that card, right? You look at that card and you have some colors. Red color, and then you have black color also, right? That mix. So with that little glimpse, you know it's a face card. Okay, you know it's a face card. Now, what is the probability that it is actually a king? What's the probability that it is a king? Let's look back into our compound event. At least you can imagine this now. Okay, so suppose you get that card, but you don't know if it is king or jack or queen. You just know that it is a face card. So you kind of have a glimpse of what it looks like here, right? Okay, if you happen to see this, oh, it must be a face card. Now, then, can you tell what is the probability it is a king? Given that it is face card, then the way we count it is the following. How many face cards do we have? We have jack, queen, king for spade, for club, for heart, for diamond, right? So we have a total of 12 face cards. Now, of these 12 face cards, how many of them king? There are 4 of them king. Now, then the probability that it is a king is now 1/3. That's because we know something else. Okay, we know something more. We are not now selecting from the whole 52 cards. We have a little knowledge that it is a face card. Okay. On the other hand, let's change this. What is the probability you get an ace? The notation is probability of ace. Probability of getting an ace is 4 out of 52. That's still the same to part A, right? Same idea. There are 4 aces out of 52 cards. Now, but what if I ask you what is the probability it is an ace, knowing it's a face card? How many face cards do we have? There are 12 face cards. Now, of these 12 face cards, how many of them ace? Zero. None of them ace. Okay, so when you play blackjack, right? When you play blackjack and you are expecting an ace, but you happen to see, oh, that's multicolors. Too many colors in that card, then it won't be an ace. It must be a face card, like that. Okay, now let's turn our view into a Venn diagram instead. Example 2, suppose I have this Venn diagram. This is circle A, and this is circle B. The one we had earlier. There are 17 elements in A, 5 of them also in B. And there are 18 elements in B. A total of 40. Let's say we have this then. Now select one element at random. So select one element from that Venn diagram. Okay. Part A, find the probability that it is the one element you select is from B. The one element you get is from B. Then there will be a total of 40. How many of them in B? There are 5 plus 13. Okay, that's 9 over 20. When I reduce that, but at least you know how you get that 18 over 40. Okay, now the result will be different if I ask, what is the probability that it is a B from B, knowing that's also in A? Okay, basically you know it is in A. What is the probability it is also in B? Then you see how many elements we have in A. We have 12 plus 5 elements in A. Right? Now, of these 17 elements in A, how many of them in B? So this notation means what? It means you select from, instead of from the whole deck or the whole Venn diagram, you only select from those in A. Okay, so that's why we have 17 on the denominator. Okay, now of these in A, how many of them in B? Okay, so you will see this will be the probability of getting B given A will be over 17, you have 5. Any questions so far? No question. Let's turn around. How about probability of selecting something from A knowing we select from B? So let's see the denominator first. How many elements we have in B? How many elements we select from? In B, there are 5 plus 13 elements, right? There are 18 elements in B. Okay. What is the probability among these 18 elements? You select someone from A. So this is what you select from. Instead of the whole Venn diagram, you select only from these 18 elements. What is the probability you end up selecting someone from here or something from there? And you will see that's equals to 5 out of 18. Okay. Now let's do 2 more problems just to make sure that we really get it. How about probability of getting selecting an element in B knowing that element is not in A? So the extra knowledge that it is not in A, how will that influence our knowledge of probability of getting something from B? And part E, what is the probability of selecting something not in A knowing it is not in B? Oh, that's a lot more difficult. No, it's not. It's doable. It's doable. Of course, you need to focus. You need to understand what those means. Okay? You need to understand what those means. Let's see. Probability of B given not A. Look at what we select from first. We select from not in A. That refers to outside of A. So this guy and that guy. Right? So there are 13 plus 10 elements outside of A. So you select from 23 elements. Now, among those 23 elements, how many of them in B? Among those outside of A, there are 23 of them. How many of them in B? There are 13 of them, right? 13 of them. So the probability of selecting B given is not in A is 13 out of 23. Last one. How about probability of selecting something not in A knowing it is not in B? Let's see the one not in B first. How many elements not in B? This is not in B. This is not in B. Okay, so there are 12 plus 10 elements not in B. So we will be selecting from those 22 elements. Now, how many of them not in A? How many of them not in A? There are 10 of them not in A, right? There are 10 of them not in A. So that will be 10 over 22, which we happen to be able to reduce. Okay. If you can reduce, always reduce. Now, you will see when it comes to computing conditional probability from a Venn diagram, then the number you have on the top will be one of the number you have at the bottom. The number you have on the top will be part of the number you have at the bottom. Okay? The number you have on the top will be part of the number you have at the bottom. Well, because it's conditional, means you are forced to select not from the whole Venn diagram, but only part of that. Okay? Now, let's see the 3 circles case. Suppose we have 3 circles. Let me find the problem. Suppose we have these. Suppose we have, for example, suppose we have this. Okay, now what I want you to do is to compute, find the probability of selecting an element from C. So you need to know the total. Let's find out what's the total. The number of elements in the sample space will be 10 plus 10, 20, 35 plus 19. Yeah, 64. The number of elements here is 64. Okay, now, but I want you to compute the following probability of selecting one element from C. How about probability of selecting an element in C given we know that person or that element is in B? Probability of getting B given it is in C. How about probability that it is in A given it is not in B? Probability that it is in C given, not in C given it is not in A. Oh, it's quite difficult. Now, let me ask you to do this together with your break. We will do the long break right now. We'll do a long break right now. We come back around 30 minutes from now. We come back at 12:10. Yeah, we come back at 12:10. Okay. Either you do this first and then you take your break, or you take your break first and then do this. If I were you, I will do this first while the material is still fresh for you. Now, after we do this problem with the Venn diagram, then we will turn our attention to what if we have a contingency table. Okay, let's continue later. Let's start again. I incorrectly referred to this section as 5.3 earlier. I confused that with the textbook we use at West LA College. It's supposed to be 4.3. Okay, it's supposed to be 4.3. Now then, this inclusion, exclusion, and compound events are basically the mixture between 4.2 and 4.3. Okay, compound events supposed to be in 4.3, you know. Okay, but the way I kind of break them up is 4.1 is the introduction, 4.2 is everything beside 4.3 conditional probability. Okay, now later on you will see that this conditional probability has something to do with the compound event that we did earlier. Yeah, either you want to see the connection or in our subconscious is actually already there. Okay, let's do this problem. Now, after I'm done with this, we will apply whatever we learned today to contingency table case. Okay, let's see. Probability of C, how many elements in C? 2 plus 7 plus 3 plus 15 over 64. That's 25. That's 27 over 64. Okay, now then part B. What is probability of selecting something from C knowing it is in B? So let's see first how many elements we have in B. There are 6 plus 4 plus 7 plus 3. There are 20 elements in B. Of these 20 elements, how many of them in C? That's 7 plus 3. 50% chance. Now, how about probability of getting an element in B knowing that element is in C? 2 plus 7 plus 3 plus 15. They are 27. Yeah, they are 27. We counted earlier. Yeah, there are 27 elements in C. Of these 27, how many of them in B? 7 plus 3. So there are 10. The probability is 10 out of 27. How about probability of not B, outside of B? Outside of B is 17 plus 2 plus 15 plus 10. How many are there? 34, 44. Of these 44 elements not in B, how many of them in A? Of these elements not in B, how many of them also in A? Right? Those are the two. Okay, so there are 17 plus 2 elements of those not in B to be in A. Now, finally, what is the probability that it is not in C, knowing it is not in A? Not in A's, those are the number of elements not in A. That's 32 elements. Oh, am I doing it? 25 plus 10, no, 35, not 32. I'm sorry, 35. Now, of these 35 elements not in A, how many of them not in C? The one not in C are these guys and these guys. Those are the ones not in C's. So there are 10 plus. Hold on. What am I doing? I think I write it wrong. Okay, 10, 15, 3, 4, not 7. Ah, good thing. Good thing I see it. So here's 4, not 7. Plus 4. So I was right. That was 32 earlier. Right now, of those not in A, there are 10 plus 4 of them not in C. Okay, which I can reduce to be 7 over 16. Okay, now conditional probability is very, very useful to update our original probability to be more contextual. Okay, to be more contextual. Now, the thing is the following, for example, I teach you how to look at that, how to use conditional probability. conditional probability allow us to be more contextual, like this. Let me use the following situation. Okay, from Thomas, from your instructor's historical grade, from Thomas grade roster. From Thomas grade roster. So of those students who took statistic with me, okay, the proportion and therefore the probability somebody passed the class is, let's say, we have, I make up numbers, okay? I make up numbers. Out of, let's say, 200 students who took my class, let's say 85 of them pass. Okay, 85 of them pass. Now, the thing is, let's say somebody took test number 1, which is for you 2 weeks from now. Okay, that's why I want you to start studying for your test 1. Look at my old test 1, go to my website, print them out, okay, try to work on that. I did a lot of them already last week, I remember. Okay, that's why together with what we did today, you should be able to do all test 1s from the past. Okay, and yes, you have a quiz that is due tomorrow. Don't forget that. Now, suppose then after the test, somebody messed up, did so bad. Okay, let's say that person end up with 40 in test 1. Okay, then that person asked me that question, Thomas, what is the probability I end up passing this class? The question sounds similar to the problem that we know in general. So if a general audience or my department chair or somebody asks me, Thomas, what is the probability somebody pass your statistic class? Then I look at my frequency distribution, and therefore I create the relative frequency. Okay, I will say, well, 85 out of 200 pass the class, right? But then if a student suddenly asks me that question, what is the probability I pass the class? Okay, so even though it sounds like just questioning what's the probability that person passed the class, but knowing that person did not pass test 1. So the context is not that we select from the general audience. We will select from those who did not pass test 1. Of those who did not pass test 1, let's say they are 100. Actually, let's say there are 120 of them didn't pass test 1. I get only 10 end up passing the class. You see, so the question of Thomas, what is the probability I pass the class, is different from each person. Because when you say I, did you ask me this with knowledge that you pass the test 1 or you don't pass test 1, or we don't even have test 1 yet? Okay, so if you ask me this question right now, Thomas, what's the probability I pass the class? Then I look at my frequency distribution, then I will tell you this. Okay, but after our test 1, after test 1, Thomas, what is the probability I pass the class? Then I ask you first, did you pass test 1? Did you pass it or not? If you didn't pass it, then your number is this. Okay, but Thomas, before the test, you say that the probability somebody passed the class is 85 over 200. That's true, but you say I, right? It refers to you who did not pass test 1. Your probability is a lot lower. Okay, so it becomes more contextual. That's why the answer you get when you ask me this question may be very different from the answer somebody else get when they ask exactly the same question, because the word I that you use there refers to different person. Okay, maybe that person did not pass test 1 and you do. If you pass test 1, the probability for you to pass the class will be different from the probability that person who to pass the class, knowing that person didn't pass test 1. Okay. Now, this also brings us to a common situation in our daily life. The one that I'm about to talk about right now is actually a discussion that I have with department chair at West LA College, the science department chair, not math department, science department chair. We have an issue that I myself acknowledge is an issue for STEM program. So all instructors in science, technology, engineering, and math all see this as an issue, that the proportion of female participation in STEM is very low. In other words, we say this: the proportion of female in college. Let's just use college as a starting point. The proportion of female in college is more than 50%. Let's say 60% for sake of simplicity. I make up numbers. Okay, but the thing is, knowing that person is in STEM program, the probability that person is actually a female is a lot lower. I think it's less than 60%, less than 40%. I make up numbers, let's say is 20%. And this 20% may be still too high. Okay, as I know, it's like around 1 out of 6 or 1 out of 7 instead of 1 out of 5. Okay, so when we compare, you know what, our college is really big, more than half of them female, right? More than half of them female. So it's supposed to be, if it is proportional, then the proportion of female in STEM program should also be around 60%. But why all of a sudden it's a lot lower? So we try to introspect ourselves, think about, you know what we can do better so that we can attract more female. Okay, now what I'm about to tell you, what I am telling you here is actually a true event. Okay, it's a true event. It is a discussion that we have, and all of us in that group that we try to fix this situation have that concern of why female participation in STEM is so low and what we can do to improve that. Okay, now, of course, my reason to be in that group and I have that concern is actually quite different from other people. And it doesn't have to be a wrong way. Okay, simply because they are different, they have different reason doesn't mean they're wrong. We have different objectives, right? But the way I see is this. One way to improve our women's pay in life is to push more women to participate in STEM. You have to agree that people who work in STEM field, science, technology, engineering, and math, have significantly higher pay. So when we look at the pay, pay parity of male and female, we say that on average, women's pay is lower compared to male, right? I have my own view. I'm not saying that it's wrong. I'm not saying that females' pay is not lower in average compared to males' pay. I'm not saying that's wrong. I agree with that, okay? But to say that it is always because that female get less pay even though they work in the same field may not be a good starting point, okay? Let me tell you why. We have to agree that even when the two female working and one of them in STEM program and the other one in non-STEM program, the pay for female or women in STEM program is higher, significantly higher. So in other words, if you want to have women on average has a much higher pay, one way we can do it, again, we can study I apologize. Sorry, my internet connection dropped earlier. I need to change the screen. Okay, so coming back to the discussion that yes, even female in STEM get better pay compared to female not in STEM. I do agree that we have situation where male in STEM has better pay on average compared to female in STEM. On average, okay? But further view tells us that the reason is the following. Male in STEMs, they tend to stay longer. So imagine if you have researchers, male researchers, already working in the field for like 30 years, okay, compared to female who work in the same field for only 20 years or only 10 years. So the reason the male is associated to higher pay is because on average, they actually work longer in that STEM field or in that company compared to their female counterpart. Okay, of course, then when we brought them into statistic, we write them down, the numbers, and we get the average, right? Basically, we get the average of the pay. It seems like female in STEM programs still get less than on average compared to the male counterparts. Okay. Now, of course, there are a lot of issues that we can do. A lot of issues that make this situation happen. Okay. Now, we are not. At least I don't see myself as somebody who can solve all the problem that using my method later on. Then everybody have the same pay already. No, I don't think that's something I can achieve. Okay, if you put that in my hand, I don't think I'm able to do that. Okay, but what I can try to do is this. What I can try to do is push more female into the STEM program. Okay, then if we have more female in the STEM program, then the aggregate, the overall female pay will improve. Okay, the gap will not be that big anymore, hopefully. Okay, now it's another thing to try. I hope somebody else can try to work on that. I will try to also help that, okay, such that my female students who are already in STEM program, okay, when they go to work later on, they can stay in that program for a longer time. You see what I mean? And if they can work for 30 years, then of course, at the end of their career, they have that the 30 years pay, right? Instead of only work, like the last pay they get is the accumulative of that 30 years instead of only 20 years. Okay, now, so let's look back into this. Given that that person is in STEM program, then the probability that person is female is actually much lower than the proportion of female in our college. Now, on the other hand, if we look at backward probability of somebody's working in STEM knowing is a female, if you know that person is a female, why I cannot write on this? What happened? Give me a second. I don't know what happened with my computer. Something not right with my computer. Give me a second. recording, right? It's recording. Give me a second. I share that there. Okay, here. Oh, I hope I'm good right now. So suppose knowing it's a female that we select from, the probability that person actually in STEM program is actually still quite low. As if there's a disassociation between our female group and the STEM group. Okay, even though not that big, but still, right? Knowing that person is a female, the probability that person in STEM program, I make up numbers again. Let's say it's 15%. So it's still low, right? Now, here's the problem. Here's start the problem. One instructor, very close friend of mine, so not about that person, it's about the idea. Okay, one instructor say this. Okay, he said he suspects that the curriculum, happened again. Oh yeah, that the curriculum, the STEM curriculum, is steered toward male students only. And therefore drives women students away, female students away. I really, give me a second. Yeah, only male students only and drive female students away. In other words, is it possible we suspect that our STEM curriculum is discriminatory toward female students? Toward female students. Okay, now my argument toward this is I don't think so. Discriminatory. Even though we can look into that further. Okay, my view is this. I have very high regard of female women. Okay, not that I underestimate them. I have never think that because you are a female, then you won't be able to do hard stuff like STEM. No, no. I can show you that approximately of those best students that I ever had in my Calculus 3 classes, of those, the best students that I have, if I need to collect them, at least half of them actually female. Okay, so no, I do not accept the notion that women cannot do math as good as male. That's not true. That's definitely not true. Okay, the fact that I have more female doing very well in my Calculus 3 class and also my statistic class. Okay, it actually refutes the fact, the notion refutes the opinion that women cannot do math as well as male. So I don't accept that argument. Okay. The one that I think I'm not saying that the curriculum is not discriminatory, but at least that's not what I see first. Okay, the way I see is the tendency. Okay, the tendency. Female students tend to be able to do more things than male. Okay, especially when it comes to multitasking skill. Male, on the other hand, tend to be linear, like male in general. Of course, not everybody, okay? I'm not talking about all the time, but in general, that male tends to be single tasking. I am someone who cannot do so many things at once. I have to do only, I tend to do, even if I have 5 things I need to do, I tend to do one by one. Female, on the other hand, are equipped with more capability to do more things at once. Like, you will not trust Thomas to take care 2 children at the same time, teach and cook. No, I cannot do that. I cannot do that. And more or less, you can hear my interaction with my children, especially at the beginning of our classes, usually, right? When my son's about going to school and I start teaching, I usually get pissed off with him for singing around me. He likes to sing. He loves to sing. Oops, hold on. Now I just share it. Okay, when was that? So it's a couple minutes ago. I'm not sharing my screen. Oh, 4 minutes ago. I'm sorry. Yeah. So yeah, I'm sorry. Good thing this is not really the topic that I just try to share with you how I use conditional probability. Okay. Coming back here. So, well, I do not have in mind that female are not capable of doing the STEM program. Not at all. Not at all. Okay. Like what I said earlier, of my top students, at least 50%, at least 50% are female. And I am known as a hard teacher at West LA College. Okay, so this refutes right away that female students cannot do math as good as male. That's so not true. Okay, my view is that female students, female in general, are able to do more things compared to male at the same time. So male tends to be single tasking, female tend to be multitasking. Now, because of that women's capability to do more things at once, okay, then women has more things, more field that she can go into. While because of the background of male, then male tends to go to a field in which they are required to do single tasking only. And one of them is math, physics, chemistry, okay, engineering. You basically need to do one thing at a time, right? While female are actually a lot better, especially when it comes to the field where you need to take care of so many things, consider so many things at once. Okay, that's why somebody say that women have that very strong intuition when her boyfriend or her husband actually cheating. They don't have evidence, but they can feel it already. Okay? That's a very, very strong intuition. Okay, you will not trust Thomas to take care of babies more than his wife. I mean, that's true though. And I mean, you don't want to say, oh, Thomas, you're just discriminatory against male. Come on, man, look at your surrounding, right? Okay. If the nurse is, you believe, you believe a female more in take care children compared to a male, right? And that's only one example. When it comes to psychology, for example, female can actually interact and help you with your, I have some psychological problem, like you know that I have depression, right? I actually get better help if my counselor, my social worker, or my psychologist are female. I mean, that's fact. That's a fact. I don't blame male to be discriminatory against male. No, it's just I know me. Okay, I know my nature. I'm not saying that all male like that. I'm not saying all female like that. But in general, that's the case, right? Okay, so because female women can do more things than male, then that 60% female in our college will go to a lot more places compared to our male counterparts. Okay, now here's the thing though. My friend who say that it's because the curriculum is discriminatory simply because of this proportion, I said, but no, you cannot say the curriculum is discriminatory simply because the proportion of female in STEM is much lower. And he say, why not? Okay, now don't forget the context is that I and these uh, uh, male colleagues are very best friends. Okay, so nothing against him as a person. We were talking and discussing about what is best to solve a problem, right? So, but I said, but I disagree with you. I said to him that you judge the program to be discriminatory simply because the proportion of male female in STEM is lower. Okay, I'm not saying that it is not true, but I will not come up with that first. Okay, now I'm talking about somebody who is actually open-minded also. So when I try to refute him, he say, Thomas, why do you say that it is not discriminatory while you see that proportion of female in STEM is lower? And this is my answer. If that is true, I think I should say, if that were true, that the curriculum is discriminatory, simply because the female participation in STEM is lower, what will you say about nursing major? The participation of male in nursing major is less than 10%. Less than that. So if you dare enough to say that STEM curriculum is discriminatory simply because the percentage here is lower, because the word discriminate is very, very harsh one. Okay, that's not something I can easily ascribe to anybody or anything. Okay, not saying that discrimination is not happen, but if it happens, it's really bad. Okay, now if you try to ascribe that to our STEM program because the female participation is lower, dare you say the same thing to nursing program? Because in nursing program, out of 40 students, you may not see even 4 male students there. Okay. In other words, if that's the case, then we need to fix nursing program first instead of STEM program. Don't you agree? Right? Okay. So simply because from that number that female participation is in STEM program is low, you cannot conclude it must be because the STEM curriculum is discriminatory. No, we know for sure that we cannot apply that same notion to nursing program, right? What about thinking this way? What makes more female in nursing program instead of male? maybe the opposite, the converse is also true, because there are so many female students going to nursing program or the likeness of nursing program, as a social study, okay, or psychology, such that then we have much less students, or much less female students available to go to STEM program. It could be the case. Okay, now the way I try to market STEM program in my classes, including your class, of course. If you do well in this stats class, consider taking more math classes. Okay, you don't need to be in math major to be called STEM program, but I have seen people coming from fashion design major. Yes, it's a girl. Fashion design major, took my statistic class. She liked it. So she took more math class. She took more math classes, more math classes. She ended up being a math teacher at Culver City High School. Okay. So imagine somebody who went to fashion design major and you think they don't do math at all, right? At all, no math. She took my statistic class simply because it was required. Okay, but strangely, she said, Thomas, when you taught statistics, I start seeing how math is related to how I make decisions in my life, right? So can I take more math classes? I say, of course, I welcome you, you know. And she took more, she took more, she took more. And like 1 year after that, she said, Thomas, I'm going to math major. Okay, I said, what? What math major? Yeah, I want to teach in high school. And I say, why you make that decision? She said this, because even if I go on in fashion design major, okay, the pay is not as good compared to if I become a high school teacher. It's more stable, and high school teacher in public school is more, yeah, a lot more stable with very good retirement package. Okay, and she did say, and I'm proud when she said that to me. She said, Thomas, it's you who changed my mind about math. Okay, and she has a much better life right now compared to what she was projected at that time. You know? So you see the analysis of this, right? Knowing why something happened enable us to see the issues we have and at least get some partial solution. At least we know. Then later on, my friend agreed with me. Yes, no, I will not go to the route of claiming it's because of the discriminatory curriculum. Okay, yeah. So I hope that brings us to see how conditional probability enable us to compute the situation in more contextual compared to if we don't have the context. So again, going back to this great roster, what is the probability that somebody passed my class? 85 out of 200. Now, what happened if that person did not even pass the first test? Then the probability that person passed the class is much lower, much, much lower. Okay. On the other hand, that's why I emphasize your test one. What is the probability you pass the class knowing that you passed test one? Then of those who pass test one, there are 80 of them among that 100. The one end up passing is actually 75. For example, I just make up numbers. Okay, let's say 40 instead. You see? Okay, if you pass test one, the chance of you end up passing this class is 50%. But if you don't pass test one, the probability you end up passing this class is much, much lower, less than 10%. Okay, even though this number here are hypothetical, but I try to give to you the actual situation. I don't remember the precise number. Okay, but I hope the number I quote here actually reflect my opinion about what you need. Make sure, please do study hard enough to pass test one. Out of 5 tests, 4 tests plus 1 final. If you pass test one, at least you have one less issue to worry, right? Okay. If you don't pass your test one, then you always have that one issue that you don't resolve. So please make sure you pass this test one. Okay. Now I will go on with other approach of looking at conditional probability. Give me a second. I will quote some contingency table. Let me quote a contingency table. Let's say we get this one here. We did this last week, but this time we changed the context to conditional probability. So let's say we have this. For example, we have this group. Okay. Let me add them to help you. So this is 37, this is 45, this is 58. A total of how many? 120, 140. And this is 49 here, 48 here, and this is 43 here. Okay, let's say we have this, and then a participant is randomly selected from the group. Write the notation and find the probability of selecting. I write the notation for you. Okay, what is the probability of selecting somebody with a bachelor? So if I select one person at random, what is the probability? The highest education of that selected person is a bachelor. Notice that this is not conditional probability. So we select from 140 people. Of these 140 people, how many of them have bachelor? The total number of bachelor is 43, right? So they are the probability to select somebody with highest education level bachelor is 43 out of 140. Now let's change the situation. Find the probability somebody actually has a bachelor in this group, knowing that person never smoked. Knowing that person never smoked. Then you look at those who don't smoke. How many people don't smoke? Yeah, 37 people don't smoke. Never smoke, right? There are 37 people never smoke. Of those 37 people who never smoke, how many of them have bachelor? There are 12 of them. How about if we go around? What is the probability somebody never smoke, knowing that person have bachelor degree? So you see how many people have bachelor? There are 43 people have bachelor. Of those 43 people who has bachelor, how many of them never smoke? 12 of them never smoke. Okay, It's that simple. It's really just that simple. You need to know what those notation means. Okay, and then as always, we always do the denominator first. How many people we select from, and the number on the numerator, how many people of this that you select from satisfy the condition, satisfy the desired situation. Okay, now let me ask you to do two problems from here. I make up some two problems, and then would like you to do part D. What is the probability that somebody is a current smoker, knowing that person has only high school diploma? And then find the probability that person actually somebody with associate degree as the highest education level, knowing that person is not a current smoker. Okay, let me give you a couple minutes to do this problem. Let's say 2 minutes. Okay, let's work in this. How many people with high school diploma as the highest education level? Yeah, 49, right? Of these 49 people who has high school diploma as highest education level, there are 15 of them current smoker. So that will be 15 out of 49. Next, what is the probability somebody have associate degree as the highest education diploma, knowing that person currently not smoking? Not a current smoker. Now, not current smoker refers to these people. Okay, so there are 37 plus 58 people currently not smoking. Okay, now of those 95 people, how many of them have associate degrees? (11 plus 16), right? 27 of them has associate degree. Of those currently not smoking, 27 of them has associate degree as their final education. Okay, now as a closing, let's do two more problem. Okay, so we will select from this group. Okay, we will select from this group, something we did earlier, but we just applied that first time to contingency table. If we select two people, find the probability that both of them current smoker. And then that's part A. Part B, find the probability that at least one has bachelor. If you select two people, what is the probability that at least one has bachelor? Let me give you 3 or 4 minutes for this. We did this before in the context of Venn diagram. Now let's see how you will do this in the context of contingency table. Not too hard though, it should not be too hard. Okay. Let me ask you to do that, maybe 4 minutes from now. And both current, then what is the probability the first person is a current smoker? That's 45 out of 140. And probability the second person, given that the first person is a current smoker. Then the probability the next person, also a current smoker, is 44 out of 139. Notice that the probability here is actually under the condition that the first one selected is a current smoker, right? Okay, so we did this type of problem earlier when we did compound event without considering probability, conditional probability explicitly. No need. Okay, we can do it by heart this way. Okay, now part B, what is the probability at least one of them, of these two people selected, has a bachelor? Then that will be 1 minus probability no bachelor, which is 1 minus probability how many non-bachelor there? 49 plus 48, that's 97. 97 over 140 times 96 over 139. Okay, 1 minus blah, whatever that is. Everything after that is calculator skill. Okay, I will stop here for our lesson today. What we will do next week, I will continue on probability, conditional probability, but the one we will do next week are into the theoretical part. Okay, let me remind you that my test one material, your test one material actually ends at compound event. Okay, that's the material for your test one. However, if you go further into my past test ones, like around 4 years ago, 5 years ago, you may see some test ones has conditional probability. Now, some test one where I have conditional probability actually cover this part. Okay, but none of my test one has theoretical view of conditional probability. Next week, that's what we will do. We'll do conditional probability from theoretical point of view. I may spend around 1 hour, 1.5 hours on that. And then I go on to counting 4.4. Okay, now I hope next week you already have your TI-84 because we will use some button from there. Okay then, see you next week.